Jai Hind everyone. I am Nikita Jaiswal from Civil Engineering Department, Ajay Kumar Garg Engineering College. And today we are going to discuss applications of Bernoulli theorem and how we can derive Bernoulli theorem, what are the applications also, and related some numericals. So, uh, before going to Bernoulli theorem, we need to understand what is the concept of energy that is contained or conserved in flowing water. So, whatever kind of energy or energy head we are going to discuss, first we need to identify it. Okay. So, the energy in general may be defined as the capacity to do work. So, whatever energy that is contained in flowing fluid, see, we can differentiate or we can categorize into three forms. Let us suppose the first one is potential energy. You know very well what is potential energy. Second is kinetic energy, and third is pressure energy. Okay. So, potential energy, it is what due to the height of flowing fluid or any particular pipe, it is situated from any, from any datum. Okay, let us suppose this is a pipe, this water is flowing, is water, flowing fluid is water. Okay, and when we talk about this particular pipe, we are going to discuss three kind of energy that is contained in inside this pipe. Okay, so first will be potential energy. Potential energy is, it is what, it is the height, from any reference level. Okay, or you can say the reference level, you can say it as datum. Okay, the second is kinetic energy. Now kinetic energy is what, so flowing fluid or flowing water may be containing some kind of maybe containing some amount of kinetic energy. And the third one is pressure energy. So whatever kind of pressure energy that is involved in that particular pipe, due to which the fluid is flowing, okay, we need to consider that type of energy also. Okay, so these three energies we are going to discuss. Now the energy that is possessed by a liquid particle by virtue of its position. Okay, so that will be your potential energy. We have talked about that. Okay, and what will be your kinetic energy of a liquid particle? Obviously the liquid particle, if it is in motion, what you will say, that particular liquid particle is having a velocity, and because it is having a velocity, there must be an kinetic energy involved in that fluid particle or flow. Okay, so here just understand what are the kinds of energy are involved in flowing fluid. Okay, third, you can say pressure energy of a liquid particle in motion. Now it is the energy possessed by a liquid particle by virtue of its existing pressure. Okay, so whatever pressure is involved in a flowing fluid, because of that fluid is flowing. Okay, so because of that involved pressure, okay, we are going to take that pressure also in consideration under category of energy. Okay, so that will be called your pressure energy. Okay, if liquid particle is under a pressure of P kilonewton per meter square, or you can say P kilonewton per meter square, you can also write it as kilopascal. Okay, then the pressure energy of the particle will be P by W meter kg per meter kg. Okay, or you can simply write it as head equal to P by rho g. Okay, or you can write it as small p by rho g meter. Okay, we are going to discuss all that terms in unit of meter. Okay, so we can call it as pressure head, we can call it as kinetic head, we can call it as potential head. Okay, so this W means rho g. Okay, now when we write the mathematical equation for total energy of a liquid particle in motion, what we are going to write? Total energy of a liquid particle in motion is the sum of potential energy, kinetic energy, and pressure energy. So mathematically total energy will be equal to your datum head, or you can say potential energy. Okay, V square by 2g, that is kinetic head or kinetic energy, whatever you want to say it, and P by W, or you can write it as P by rho G as your pressure head. Okay. So, again, if there is an inclined pipe and you are taking two sections, let us suppose this is section number 1 and this is section number 2, there is a datum. Okay, you have taken it as your reference line or datum line. Okay. And those two sections, if you consider central line, okay, for section 1, this will be your, let us suppose, datum 1, or you can say is as a potential energy, or you can say that this particular section having Z1 potential energy. Okay. And what will be the value for potential energy or datum energy at section 2? Let us suppose this is Z. Okay. Now, whatever fluid is flowing in this pipe, let us suppose that having a velocity and average velocity of V. Okay. Now, the kinetic energy, obviously kinetic head will be equal to your P square V square by 2G. Okay. Let us suppose this section is also having a pressure of small p. So, your pressure head will be equal to, if this section, if you are considering section number 1, let us suppose P1 is here and let us suppose P2 is here. Also, let us suppose that the pipe is not symmetrical at all. So, what you are going to say again, that at section 1 velocity may be V1, velocity at section 2 may be V2. Okay. So, when you write equation for section 1, equation for total energy for section number 1, okay, what you are going to write it as E1 equal to P1 by rho G plus V1 square by 2G plus Z1. Okay. In a similar manner, you are going to write equation for E2 also. So, this will be equal to your P2 by rho G plus V1 square by 2G plus Z2. Okay. So, we can write the equation for total energy in this way for any section. Okay. We have considered only just 2 sections, but you can write for a number of sections. Okay. Now, we have formulated the same in terms of head. Okay. The equation will be same, but in this case all that terms containing unit of meter. Okay. Here also in unit of meter. Now, what Bernoulli says about the total energy contained or conserved in any section in moving fluid. Okay. What Bernoulli says, that at any section in flowing fluid, okay, that particular fluid should be perfectly incompressible. Okay. And so, when we talk about the total energy of any particle, that be same for any section, or let us suppose from the previous slide, if we are considering a single fluid particle here. Okay. We are tracking its motion. So, when that particular fluid particle was in section number 1, we have written equation for total energy. When that particular fluid particle reaches to section number 2, we also have written equation for total energy. What Bernoulli says again, that the equation for section 1 and section 2, the equation, or you can say the total energy at section 1 and section 2 must be equal, or you can say the energy contained or total energy contained in a flowing fluid must be constant. Okay. That is the simple answer for Bernoulli equation, but there are some assumptions. He have assumed that that fluid or flowing fluid must be incompressible. Okay. Must be a continuous stream. So, there are some assumptions involved in this statement, but the total conclusion, the overall conclusion is same, that energy contained, energy conserved must be constant from section to section. Okay. So, again there are another assumption, assumption that there should be no losses due to friction in the pipe. Okay. So after all assuming or those assumptions, we can write that the energy equation must be constant. Okay. So here again Z is your potential energy, P square by 2G is your kinetic energy, and P by W is your pressure energy. Okay. Now just consider a section of pipe. Here you can see the section number 1 here, section number 2 here. Okay. On both the sections there are some pressures are acting, pressure intensities are acting. Okay. So let us suppose the pressure at section 1 is P1. Okay. And section S and pressure at section 2 is your, this is P2. Okay. P2. Also we have considered the height, the datum height of both the sections. Okay. Okay. Now if we write equation for pressure force, you know very well what is the equation for pressure force is equal to pressure intensity multiplied by area of pipe. Okay. If you are giving, if you are having pressure force and you need to convert in pressure intensity, it is divided by area of pipe. Okay. Now we are going further. So that we have just discussed what is the basics of Bernoulli equation. Okay, we have just studied the statement, but actually that Bernoulli equation comes from came from Euler's equation of for motion. Okay. Now Euler has also given some equation on the basis of some assumptions again involved in flowing fluid. Okay. Now the Euler equation, Euler's equation for steady flow, again steady flow, okay, for an ideal fluid along with streamline is based on Newton's second law of motion. Okay. The integration of equation gives Bernoulli equation in the form of energy per unit weight of the flowing fluid is based on the following assumptions. So the Euler's equation, Euler have given an equation which is again for steady flow and steady flow of an ideal fluid. Okay. Again that particular fluid should be streamlined. So there were some assumptions. You also need to understand what are those assumptions. The first one is the fluid should be non-viscous. Okay, non-viscous. The second is the fluid is homogeneous and incompressible. Third is the flow is continuous, steady and along the streamline. Fourth is the velocity of flow is uniform over the section. And the fifth is no energy or force is involved in the flow. Okay. So this assumptions should be there, this conditions should be there, then only you can write equation for Euler's equation, equation for Euler's energy equation. Okay. Now let us see, again there is a pipe of uniform cross section, you can see. Okay. The two sections we have taken. Okay. One is having pressure of small p, another one is having p plus dp. Okay. The datum difference between section 1 and section 2 is dz. Okay. And the length or difference between section 1 and section 2 in terms of length is your ds. Area of pipe, the small area of pipe is dA. Okay. And the V will be obviously will be your velocity in flowing fluid. So what will be the summation of total forces in x direction or in flowing fluid direction, you can say, or in the direction of streamline, you can write the formula like this. Just because the pressure at section 1 and pressure at section 2 are in opposite direction, okay, just sum it, you will going to get it as minus dp multiplied by dA. Okay, your dA is what? Your small area. Okay. Now the weight of fluid element will be what? Rho g dA ds, simple. And when we are going to resolve it, okay, that particular weight in component of the weight of the fluid element in direction of flow, okay, you are going to get it as the equation minus rho g dA ds cos theta. Now convert the cos theta in terms of dz and ds. Okay, you are going to get it as minus rho g dA ds. Mass of fluid element will be what? Your rho dA ds, or you can say rho kg per meter cube multiplied by, you can put volume dA multiplied by ds. So you are going to get it. We see the acceleration of the fluid element. Okay. The next is acceleration. What will be your acceleration is dv by dt. convert it in form of velocity and difference in velocity gradient in terms of space. Okay, so you are going to get it as v dv by ds. So just equate all the terms in equation of force. Force equal to mass multiplied by acceleration. Force you have just calculated, mass you know, and acceleration you have just calculated, you have just derived. Okay, to solve it, you are going to get an equation, or this final equation is actually your Euler's equation of motion. dp by rho plus g dz plus v dv equal to 0. Okay, just integrate it to get the Bernoulli equation. Okay, we are going to integrate it. Okay, we are just going to solve it further. Okay, okay, you are going to get the equation in this form, then again in this form. Okay, here w is your what, rho g. Okay, so finally you are going to get the Bernoulli equation in this form, that p by rho g plus z plus v square by 2g is constant. Okay, or in another words, if you are taking two sections, what Bernoulli equation says, that at section 1 energy contained should be equal to the energy contained in section number 2. Okay. Now, what are the limitations of Bernoulli theorem? The limitations of Bernoulli theorem is nothing but the assumptions involved from the starting. Okay, from the starting, that Bernoulli equation actually started from what? Euler's equation. So, whatever assumptions involved in Euler's equation was actually have gone through to the Bernoulli equation too. Okay. So, this is simple, we are going to skip it. Now, there is a problem. Okay, there is a problem. Problem number 6.1 we have taken that problem from your book R.K. Bansal. Okay. Now, problem 6.1 states that water is flowing through a pipe of 5 centimeter diameter. Okay, diameter is given as 5 centimeter. Okay, under a pressure of 29.43 Newton per centimeter square. Okay, in bracket they have mentioning that is gauge pressure with a mean velocity of 2 meter per second. Again, what you can write it as, velocity as 2 meter per second. Okay, find the total head or total energy per unit weight of the water at a cross section which is 5 meter above the datum line. Okay, the question is asking for total head or total energy per unit weight of water. Okay, or just you need to calculate the total energy by simply putting the formula. Okay, now the last line also states that the pipe section is actually 5 meter above the datum line. So in this question directly you have the value of z as 5 meter. So just simply solve it. Okay, the diameter for pipe is what, 5 centimeters, that will be equal to a 0.5 meter. Pressure is given as 29.43 Newton per centimeter square. So convert it in Newton per meter square by multiplying by 10 to the power 4. Okay, so here, and velocity is your 2, z is 5. So total energy will be what? Pressure head. Okay, pressure head plus kinetic head plus datum head. Okay, so calculate each term step by step. Okay, so pressure head will be equal to P by rho g. Pressure is given, rho you know for water, the value for rho is 1000, value for g is universal 9.81. So find out the formula for pressure head, that will be equal to a 30 meter. Okay, now go to the next term, kinetic head. So kinetic head will be equal to your v square by 2g. So here velocity is given, 2 multiplied by 2 divided by rho divided by 2g. Okay, so this will come out as your 0.204 meter. Okay, and z is given as 5. Okay. So put in the formula for total head or total energy, v by rho g plus v square by 2g plus z, that will be equal to your 35.204 meter. Okay. Now the next question, The water is flowing through a pipe having diameters 20 centimeter and 10 centimeter at a section 1 and 2 respectively. Okay, this is your 20 centimeter and this is your 10 centimeter. Okay, now the rate of flow through the pipe is 35 liters per second. Here in this question, Q is given as 35 liters per second. Okay. Now the section 1 is 6 meter above datum and section 2 is 4 meter above datum. The datum line, or you can say that the potential energy, datum energy is also given for both the sections. If the pressure at section 1, okay, is 39.24 Newton per centimeter square, find the intensity of pressure at section number 2. Okay. Now everything is clear, that the diameter is given, the datum is given, the pressure at section 1 is given, then question is asking the pressure at section number 2. Okay. Now here just going to solve it for section 1 and section 2. Section 1, the diameter is given as 0.2 meter. So now put in the equation for area, you will be getting as pi by 4.2 whole square. Okay, and P1 is equal to 39.24 Newton per centimeter square. Convert it in Newton per meter square. Okay, you need to convert all the units in SI form, okay, or SI unit. And Z1 is also given. And now go to the section number 2. Here D2 is here. Now you can calculate A2. Z2 is also known to you. You just need to calculate pressure at section number 2. Okay, rate of flow is also given 35 liters per second. That will be equal to your 0.035 meter cube per second. Now because we do not know the velocities, okay, velocity as section 1 and section 2, we just need to put discharge in continuity equation. Okay, so what is continuity equation again? Q will be equal to your A1 V1 equal to A2 V2. Simple. So just put Q here. Okay, solve it for V1. Area 1 is also you have calculated. Again solve for V2. Here area 2 is calculated. Okay, now just put all those parameters in the formula. You are going to get it as V1 as 1.114 meter per second and V2 as 4.456 meter per second. Okay, now you know very well what is V1 and what is V2. Now apply the Bernoulli equation at section 1 and section 2 simply. Okay, just put the equation. Okay, and you know very well what is P1, okay, by rho g you know very well. So put in this equation V1, you know what is V1, 1.114 square by 2g, and Z1 also known to you. Here in the same equation P2 is question mark for you. Okay, rho g you know, V2 you know, 2g you know, Z2 you know very well. Okay, put all the given terms or calculated terms in this equation, solve it for P2. And finally you are going to get it as P2 as 41.051 multiplied by 981.10 Newton per meter square, or you can write it as 40.27 Newton per centimeter square. Okay, so this is how we can calculate any kind of formula. Okay, in chapter of Bernoulli equation, all the formulas, all the equations are identical actually. You need to apply the formula. Okay, now again consider this question, problem 6.5. Water is flowing through a pipe having diameter 300 and 200 mm at the bottom and the upper end respectively. The intensity of pressure at the bottom end is given and pressure at the upper end is given. Okay, so simply the pressure at 1 and pressure at 2 is given. See here in this example the figure is given. The figure is given, that's why you can easily you can see and put in the equation, but sometimes in exam maybe there are very fewer chances to come the figure with the question. Okay, you need to draw it by yourself. Now diameter at 1 is given, diameter at 2 is given. Now the rate of flow is given as 40 liter per second. You know what is D1, you know what is P1, you know what is D2, what is P2. Okay. Determine, what was the question? Determine the difference in the datum head. Difference in the datum head, they are asking for Z2 minus Z1. Okay, or is Z1 minus Z2. So let us suppose Z2 minus Z1. If the rate of flow through pipe is 40 liters per second. Okay. Now just convert the rate of flow in meter cube per second. What will be your value? 0.04 meter cube per second. Okay. Now the rate of flow, put equation for continuity. Okay, and find out the value for V1 and V2 simply. So V1 will be what? Q1 divided by A1. In the same way, V2 will be what? Q2 divided by A2. Okay. So V1 will be equal to your 0.5658 meter per second. In the same way, your V2 will be equal to 1.274. Okay. Now simply apply Bernoulli theorem in both the sections. Okay. Just put P1 by rho g, V1 square by 2g, Z1 you do not know what is the value for Z1, V2 by rho g, V2 square by 2g, and also you do not know value for Z. Okay. Put all those parameters, all those equation, the values in this particular equation. Okay. Solve it for Z2 minus Z1 or Z1 minus Z2, whatever you want to solve it for. Okay. Now after solving, you are going to get it as Z2 minus Z1 as equal to 13.70 meter. This will be your answer for this problem. Now the next question, what is the next question states that the pipe of diameter 400 mm carries water at a velocity of 25 meter per second. The pressure at point A and B at point A and B is given as 29.43 and 22.563 Newton per centimeter square respectively, while the datum head at A and B are 28 and 30. Okay. Now the question is asking, find the loss of head between A and B. Okay. We have seen that how the total energy at section number 1 and section number 2 are same by according to Bernoulli theorem. But in actual condition, all those assumptions that was involved in the derivation of Bernoulli equation, it is not at all verified and in actual situation. Okay. So we say, or we can formulate that there may be some kind of head loss also associated with the flow at section 1 and section 2. Okay. So when we associate head loss, how we are going to write the equation, the same equation? Let us suppose E1 is total energy at section number 1, and okay, and E2 at section number 2 plus HL. Or by meaning of this equation, that if flow goes in this direction, like okay, like this is your section 1 and section 2, flow is going or movement or direction of flows from section 1 to section 2. So with the direction of flow, there must be a head loss. Okay, there must be a head loss associated in the direction of flow. Okay, then now again we are going to that particular problem. Here D is given as your 0.4 meter, velocity is given. Okay, just you need to calculate in the same way. How you are going to calculate the energy at section A? Simply pressure head plus velocity head plus datum head. Okay, put equations in this form and you are going to get an answer for EA at 89.85. Similarly, solve for section number 2 or point B. Okay, solve it. We are going to get an answer for total energy at point B as 84.89. So what will be your head loss? Simply EA minus EB or E1 minus E2. So in this, for this particular question, you are going to get it as EA minus EB as 5 meter. Okay. So, this is all for today's lecture. We are going to discuss in this Bernoulli equation, the application of Bernoulli equation in next lecture. Okay. Jai Hind everyone.